Now let us move on to the next concentration term. It is called molality. Notice the L here. And by definition, it is the number of moles of solute or the amount of substance of solute per kilogram of solvent. Pay attention to this. Molality is expressed with respect to the mass of the solvent, not the mass of the solution. And molality is denoted by the letter small m, and here is the expression for molality. It is the ratio between amount of substance of solute or number of moles of solute and mass of the solvent in kilograms. Amount of substance has the unit mole, and in the denominator we have mass in kilograms. So the unit of molality is mole per kilogram. See, molality is the ratio between amount of substance or number of moles of solute and the mass of the solvent. Amount of substance, that is number of moles, and mass are both independent of temperature and pressure. They do not change with temperature and pressure. Therefore, this ratio is also independent of temperature and pressure. So, molality of a given solution does not change with temperature and pressure. Now the question is, where is this concentration term molality used? Remember, we started discussing about solutions because it is easier to carry out some chemical reactions in solutions. Remember, instead of mixing solid lead nitrate and solid potassium iodide to carry out a chemical reaction between them, we first dissolved lead nitrate in water to prepare an aqueous solution of lead nitrate, and similarly we dissolved potassium iodide also in water to prepare an aqueous solution of potassium iodide. Then we mixed these aqueous solutions to carry out a chemical reaction between them easily and quickly. So that is the reason we started discussing about solutions. Now, when we mix different solutions to carry out chemical reactions, chemical reaction actually takes place between the solutes of the solutions. So, it is to help the solutes to mix easily with one another that we prepare solutions to carry out chemical reactions easily and quickly. So, there our focus is on the solutes because it is between the solutes of the solutions that a chemical reaction takes place. But chemical reactions are not the only reason for which solutions are prepared. Solutions are prepared for many different reasons. Earlier we understood that when a solute is dissolved in a solvent, the solvent somehow breaks the attractive forces present between the particles of the solute and thereby allow these particles to move away from one another. And because of that, the solute particles move freely in the solution. That is the effect of the solvent on the solute. That is what the solvent does to the solute during the formation of the solution. Now my question is, does the solute also have any effect on the solvent? Of course it does. The solute that is dissolved in the solvent changes certain physical properties of the solvent, like its freezing point, boiling point, vapor pressure, etc. And these are known as colligative properties. The interesting thing with these colligative properties is that they depend only on the number of solute particles present, not on the nature of the solute particles. So colligative properties like change in freezing point, boiling point, vapor pressure, etc. depend only on the number of solute particles present in a given amount of the solvent, and they do not depend on the nature of the solute particles. So for solutions that are prepared to study these colligative properties, molality is the right concentration term. Molality is an appropriate concentration term to express the concentration of solutions that are prepared to study the colligative properties, because molality represents exactly that. It is the ratio between the number of moles of solute and the mass of the solvent. So it represents the number of moles of the solute present in a given amount of the solvent. Number of moles is nothing but a measure of number of particles, right? If you multiply number of moles with Avogadro's number, you will get the number of particles. So molality represents the number of particles of solute present in a given amount of the solvent, and that is exactly what we need to study the colligative properties of solutions. So in this case, molality is the right concentration term. So now we understand where this concentration term molality is used. It is used to study the colligative properties of solutions. Now let us work out a few examples on molality. This question says fructose is the sweetest sugar. How do you prepare 450 grams of 0.1 m? Small m is the symbol for molality. So how do you prepare 450 grams of 0.1 molal aqueous solution of fructose? So obviously here the solute is fructose and the solvent is water, because we have to make an aqueous solution of fructose. So to answer this question, we have to figure out the masses of water and fructose that must be combined to prepare 450 grams of the solution with this concentration. So we are given Ma plus Mb, that is the mass of the solution. It is given as 450 grams. In kilograms it would be 0.4500. And in the question we are neither given the mass of the solvent nor the mass of the solute. We have to figure them out both. And we are also given the molality small m of the solution. It is 0.1 and the unit for molality is mole per kilogram. Now what is the expression for molality of a solution? It is equal to the amount of substance of solute over the mass of solvent in kilograms, right? Amount of substance is nothing but the number of moles. How do you get the number of moles of solute NB? If MB is the mass of the solute, to get the amount of substance, you have to divide the mass of the solute with its molar mass. Molar mass of a substance is nothing but its relative molecular mass expressed in gram per mole. The molecular formula of fructose is C6H12O6. If you calculate its relative molecular mass, it comes to be 180 approximately. So, the molar mass of fructose is 180 gram per mole. Because everything else here is in kilograms, we have to convert this also into kilograms. Can we do that? We have to divide this with 1000, right? So it would be 0.1800 kilogram per mole. That is the molar mass of fructose. So NB is equal to MB over 0.1800 kilogram per mole. Now if this is in kilograms, understand that you will get the value of MB also in kilograms. Now what is the mass of the solvent, that is MA? We know the mass of the solution, that is MA plus MB, that is 0.4500 kilograms. Then MA will be equal to 0.4500 minus MB kilograms. Understand that you will get the value of MB in kilograms. Now substitute these three values in this expression. So 0.1 mole per kilogram is equal to MB over 0.1800 kilogram per mole over 0.4500 minus MB kilogram, right? So this will be equal to MB over, these two terms will end up in the denominator, right? So it would be 0.1800 kilogram per mole multiplied with 0.4500 minus MB kilogram. Now if you take kilogram inverse to the denominator, it becomes mole over kilogram, right? That is mole per kilogram. So cancel this kilogram and this kilogram, and mole inverse when it goes to the numerator becomes mole, so these two also get cancelled. Then you will have 0.1 is equal to MB over 0.1800 multiplied with 0.4500 minus MB kilograms. Now if you simplify this, you will get the value of MB in kilograms. I will leave the simplification to you. Once you know the value of MB in kilograms, you can figure out the value of MA also in kilograms. It is nothing but 0.4500 minus MB. So that is how you will figure out the mass of the solvent and the mass of the solute to prepare 450 grams of aqueous solution of fructose with this concentration. And the next question says, glucose found in fruits is also known as blood sugar because it is present in blood and is body's primary source of energy. What is the molality of a solution that contains 36 grams of glucose in 250 grams of water? I think this is a straight question. Obviously here the solute is glucose, so MB is 36 grams. And solvent is water, so MA is 250 grams. Now, what is the expression for molality of a solution denoted by small m? It is equal to amount of substance of the solute, or in other words, number of moles of solute over mass of the solvent in kilograms. Now, how do you get the number of moles or amount of substance of solute given its mass? To get the amount of substance, you have to divide the mass given with its molar mass. The molecular formula of glucose is C6H12O6. And if you calculate, its molar mass comes to be approximately 180 gram per mole. So you have to divide 36 grams with 180 gram per mole, and if you take mole inverse into the numerator, it becomes mole. So this is the amount of substance of solute or the number of moles of solute. What is the mass of the solvent? That is water in this case. It is 250 grams, but we have to substitute mass of the solvent in kilograms. So convert this into kilograms. It would be 250 grams over 1000. That would be, it is 250 kilograms over 1000. That would be 0.2500 kilograms. So substitute these two values in this expression. So it would be 36.0 over 180 mole over 0.2500 kilograms. Simplify this to get the molality of this solution in mole per kilogram. Now the next question says, an aqueous solution of ethylene glycol is added as an antifreeze to car radiators in cold environments. See, in cold countries, particularly in winter months, the outside temperature often drops below 0 degrees centigrade. Now what happens to the water present in the car radiators when the temperature falls below 0 degrees centigrade? Obviously, it freezes into ice. But when water freezes into ice, it expands. That is, its volume increases. And because of this increase in volume, a pressure is created on the walls of the radiator and the connecting tubes. Because of this, over a period of time, the radiator and the connecting tubes develop cracks. So eventually they get damaged. Now what can we do to prevent this damage? Obviously, you should prevent water from freezing even when the outside temperature falls below 0 degrees centigrade. How can we do this? Simple. By dissolving some solutes like ethylene glycol or propylene glycol in water. When you do that, the freezing point of water decreases. Say by dissolving sufficient amount of ethylene glycol in water, we dropped the freezing point to minus 17 degrees centigrade. The freezing point of water, I meant. Now what does this mean? This means now water does not freeze until the outside temperature falls below minus 17 degrees centigrade. And ethylene glycol is known as antifreeze because it is added to water to prevent the freezing of water as much as possible by reducing its freezing point. Now the question says 620 grams of ethylene glycol is mixed with 720 grams of water. Now what is the solute and what is the solvent? You don't always have to go by the masses of the solute and the solvent. Here we are adding ethylene glycol to water for the purpose of changing its freezing point. So the substance whose properties are changed is the solvent when you are calculating molality. So here the solvent is water. So the mass of the solvent given is 720 grams and the mass of the solute given is 620 grams. And the molality denoted by small m is nothing but the ratio between the number of moles of solute or the amount of substance of solute and the mass of the solvent in kilograms. Now you know how to figure out the number of moles of solute or the amount of substance of solute, and you know how to convert the given mass of the solvent into kilograms. So I will leave it as an exercise for you. And this is the molecular formula of ethylene glycol to figure out its molar mass. Now let us take a quick recap of the three concentration terms we discussed so far. The first one is percentage by mass. It is denoted by m/m to indicate that it is a ratio between two masses. And this tells the number of parts of solute present in 100 parts of the solution by mass. And by one part, I mean a unit mass. It could be 1 milligram or 1 gram or 1 kilogram or something else. And it is dimensionless, it is independent of temperature and pressure. And it is used to express the concentrations of commercial solutions, stock solutions, etc. The second one that we discussed was mole fraction. It is denoted by capital X, and the mole fraction of a component in a solution is the ratio between the number of moles of that component and the total number of moles of the solution. Again, this is also dimensionless, independent of temperature and pressure. One application of mole fraction is in calculating partial pressures of gases. The third one that we discussed was molality, and it is denoted by the letter small m, and this tells the number of moles of solute present in 1 kilogram of the solvent. Here Nb is the number of moles of solute, Ma is the mass of the solvent in kilograms. So it has the unit mole per kilogram. It is also independent of temperature and pressure, and it is used in the study of colligative properties of solutions. Now, one interesting similarity between these three concentration terms is that directly or indirectly, they all depend on the masses of solute, solvent, solution, etc. Here you may say that we are using number of moles. Remember, for a given substance, number of moles depends only on its mass. So we are indirectly referring to mass again here. Because of that reason, they are all independent of temperature and pressure, because mass does not change with temperature and pressure. And because of the same reason, these concentration terms can be easily converted from one to the other. If you give me the percentage by mass of a solution and tell me what the solute and solvent are, I can easily calculate its mole fraction. Similarly, given the percentage by mass, I can easily calculate its molality, and the vice versa. Now you may be wondering that we originally started talking about solutions and various concentration terms for the purpose of carrying out chemical reactions in solutions. And so far we discussed three concentration terms, and we said the first one, that is percentage by mass, is appropriate for commercial solutions, stock solutions, etc. Mole fraction is used in case of partial pressures of gases, and molality for colligative properties. Now our question obviously is, which of these three concentration terms is convenient and appropriate to express the concentrations of solutions that are prepared for carrying out chemical reactions? And the answer is none of them. None of these three concentration terms is appropriate for solutions prepared for carrying out chemical reactions. So we have to come up with another concentration term that is appropriate for solutions meant for carrying out chemical reactions. And that is what we are going to discuss now. And that is called molarity. Pay attention to this letter R. This name is very similar to molality that we discussed before. It is going to be a little bit confusing. This concentration term is called molarity. And by definition, it is the amount of substance of solute or the number of moles of solute per 1 liter of the solution. So molarity tells the number of moles of solute present in 1 liter of the solution. And molarity is denoted by the letter capital M, and it is the ratio between amount of substance of solute or the number of moles of solute and the volume of the solution in liters. And you know, amount of substance has the unit mole and volume of the solution has to be in liters. So molarity has the unit mole per liter. And the interesting thing here is, though amount of substance, that is number of moles of solute, is independent of temperature, the volume of the solution depends on temperature. Therefore, molarity of a solution changes with temperature. It is not the same at all temperatures and pressures for a given solution. Pay attention to this. Molarity is temperature dependent because the volume of the solution changes with temperature. Now let us denote the amount of substance of solute or the number of moles of solute with NB and the volume of the solution with capital V. Remember, it has to be in liters. So this is the expression for the molarity of a solution denoted by capital M. Now let us consider this chemical reaction again between solid lead nitrate and solid potassium iodide. Now For stoichiometric calculations, what is it that you need? You need to know the number of moles of lead nitrate and potassium iodide that you have mixed with one another, right? And if the reaction is carried out between their solids, you can easily calculate the number of moles if you know their masses. You divide the mass with its molar mass or its relative molecular mass or formula mass in grams, you get the number of moles or amount of substance. But here I am not carrying out the reaction between the solids. I am carrying out the reaction between their aqueous solutions. See, whether you carry out the reaction in aqueous solution or between the solids directly, for stoichiometric calculations, you always need the number of moles. But how do we figure out the number of moles of lead nitrate present in the aqueous solution I have taken? Similarly, how do I figure out the number of moles of potassium iodide present in the aqueous solution I have taken? We did not have that problem in this case because we can directly measure their masses because they are pure substances, measure their masses and convert the masses into number of moles. But that is not the case here. Here I am carrying out the reaction between their aqueous solutions. So somehow I must be able to figure out the number of moles of each of these reactants present in their aqueous solutions. How can we do that? Simple. Look at this expression. To get the number of moles of solute, you have to simply take this volume to the other side, then it becomes the product of molarity of the solution and the volume of the solution in liters. And I can easily measure the volume of the solution I have taken for the reaction in the laboratory. This is not a big deal. And if you know the molarity of the solution that you are using, then the product of these two will give you the number of moles of the solute or the number of moles of the reactant. So it is so easy to figure out the number of moles of solute present in a solution if you know the molarity of the solution, because the volume of the solution can be easily measured in the laboratory. That is why molarity is the most appropriate and convenient concentration term to express the concentration of solutions prepared for the purpose of carrying out chemical reactions. See, just by multiplying the molarity with the volume of the solution in liters, you will directly get the number of moles of solute present in the solution, and this is what you need for your stoichiometric calculations. Now we are ready to work out some examples on molarity. Now this question says, how do you prepare 500 milliliters of 1 molar aqueous solution of sodium chloride? Remember, capital M represents molarity. So molar, the last letter here is R. Instead, if I say 1 small m, remember small m represents molality, therefore it is 1 molal solution. Here the last letter is L, but here the last letter is R. 1.0 capital M means 1 molar solution. 1.0 small m means 1 molal solution. Pay attention to that. Now how do we answer this question? Here obviously the solute is sodium chloride and the solvent is water because we have to prepare an aqueous solution. And to answer this question, you need to figure out the mass of sodium chloride needed to prepare this solution and the volume of water required to prepare this solution. If you can figure these two things out, then you answered the question. Now, what is the information given to us? We are given the volume of the solution in milliliters, but molarity is expressed with respect to the volume of the solution in liters. So you have to convert the given volume of the solution into liters, and that would be 0.5000 liters. And we are given the molarity of the solution, it is 1.0, and the unit for molarity is mole per liter. Don't forget the unit. Now the expression for molarity is the amount of substance of solute or the number of moles of solute over the volume of the solution in liters. Then the number of moles of solute or the amount of substance of solute is given by the product of molarity and the volume of the solution. Molarity is given as 1.0 mole per liter and volume in liters is 0.5000 liters. These two get cancelled, and simplify this to get the number of moles of solute, in this case that is sodium chloride. Now if you want to get the mass of solute, you know how to do that. Multiply the amount of substance or the number of moles with its relative formula mass expressed in grams. What is that? 23 plus 35.5. Is it 58.5? So this is the relative formula mass of sodium chloride. So if you multiply the number of moles of sodium chloride with its relative formula mass expressed in grams, you will get the mass of sodium chloride. So we already figured out the mass of sodium chloride required to prepare this solution. Now the question is, we have to figure out the volume of water needed. Now our intuition says that to make 500 milliliters of this solution, dissolve this amount of sodium chloride in 500 milliliters of water, right? So if I say to prepare 500 milliliters of 1 molar aqueous solution of sodium chloride, you have to dissolve so much of sodium chloride, so many grams of sodium chloride in 500 ml of water. Is this statement correct or not? See, if we pay a little attention to this statement, we might feel that this statement is wrong. That is because the solute, in this case sodium chloride, needed for the preparation of this solution itself has some volume, though it is very small compared to the volume of water needed for the preparation of this solution. Every substance has some volume, more or less. So if we say the volume of the solute is Vb, and if you try to mix this solute with 500 milliliters of water, then again our intuition says that the volume of the resulting solution is more than 500 milliliters, right? If you add some value, however small that is, to 500, then you will get a value bigger than 500. So this is what our intuition is saying, and because of that you would say that this statement is wrong. See, we have to prepare exactly 500 milliliters of this aqueous solution. But if you add 500 milliliters of solvent to this solute, which has some volume by itself, then going by our intuition, the volume of the solution must be more than 500 milliliters, in which case this statement is wrong. Then what is the correct statement? if you think mixing the solute with exactly 500 milliliters of water is wrong because the resulting solution will have more than 500 milliliters volume, then what is the correct statement? Let us see. Let us say the volume of the solute is VB and the volume of the solvent needed is VA. And because we are preparing 500 milliliters of the solution, our intuition says that VB plus VA must be equal to 500 milliliters. Then VA, that is the volume of the solvent, in this case water needed, will be 500 milliliters minus VB. So, if you somehow know the volume of solute or the sodium chloride that is needed for the preparation of this solution, subtract it from 500 ml to get the volume of water needed for the preparation of this solution. Now my question is this statement true at least? See, this statement would be true if our intuition is correct. That is, if the volumes of the components of a solution are additive. That is, if the volume of the solution is equal to sum of the volumes of the solvent and the solute. But there is no such law that says that the volume of the solution must be equal to the sum of the volumes of its components. There is a similar law for mass, that is, the mass of the solution is equal to the mass of the solvent plus mass of the solute. This is law of conservation of mass. And there is no such thing as law of conservation of volume. So, this may not be true. That is, the volume of the solution is equal to the volume of the solvent plus the volume of the solute. In the preparation of some solutions, there is an increase in volume. In the preparation of some solutions, there is a decrease in volume. Sometimes this might hold good. So, it entirely depends on the nature of the solute and the solvent, and because there is nothing like law of conservation of volume, we cannot come up with a relationship between the volume of the solution and the volume of the solvent and the solute. Because of this reason, I cannot tell whether this statement is true or false, or this statement is true or false, or if both are false. So what I am saying is, sitting at my desk, I cannot calculate the volume of water required to prepare 500 milliliters of this solution with this concentration. Then what is the correct statement? See, one thing I know for sure is the mass of solute or the mass of sodium chloride in this case required to prepare this solution. I figured that out here. So I know the exact mass of sodium chloride needed for the preparation of this solution. But I do not know either the volume or the mass of water needed. So in that case, what would I say? I would only say that mix this solute or sodium chloride with sufficient amount of water. What do you mean by sufficient amount of water? Whatever it is. Mix it with as much water as needed to make 500 ml of the solution. That's all I can tell you. Sitting at my desk, I cannot tell you the quantity of water needed for the preparation of this solution. But I can tell you the mass of the solute needed for the preparation of this solution. Now, if that is the case, how can we ever prepare this solution? Go to a laboratory to do that. In a laboratory, we can prepare solutions of required molarity with the help of an apparatus called volumetric flask. A volumetric flask has a particular volume at a given temperature, and this is how it looks like. And you will find volumetric flasks with different volumes or different capacities. And this is called the neck of the volumetric flask, and on the neck you will find a ring etched in glass. This ring or this marking indicates the volume of the liquid present in the flask. If you fill this flask with a liquid up to this marking, then the volume of the liquid in the flask is equal to the capacity of the flask or the volume of the flask. Now here we wanted to prepare 500 milliliters of the solution, right? So you pick a volumetric flask that has a volume of 500 milliliters. Take an empty volumetric flask with this volume, and you know the exact mass of sodium chloride needed to prepare this solution. We calculated that here. So take that many grams of sodium chloride and place it in an empty volumetric flask, and then start adding water in small amounts until all the sodium chloride has completely dissolved. After that, keep adding more and more water until the water level reaches this marking. So what do we have in this flask? A homogeneous mixture of sodium chloride and water. That is an aqueous solution of sodium chloride. And what is the volume of this solution? Because we filled the flask up to this marking with water, the volume of this solution is exactly equal to 500 milliliters. That is the volume of the flask. So here we have exactly 500 milliliters of an aqueous solution of sodium chloride that has 1 molar concentration. And how did we prepare this? We know the exact mass of sodium chloride needed to prepare this solution. So we measured the mass of sodium chloride and placed the right amount of sodium chloride in an empty volumetric flask, and then we added sufficient amount of water to make 500 ml of the solution. That is how we prepared it. Now you may ask, does it not bother you that you do not know the volume or the mass of water needed to make 500 ml of this solution? All we are saying is add sufficient amount of water, and I still do not know the volume or the mass of water needed to make this solution. Does it not bother you? No, it does not, because this concentration term is used to figure out the number of moles of solute present in the solution. And I can figure that out if I know the molarity of the solution and the volume of the solution taken. Because I can easily measure the volume, if I know the molarity, I can easily figure out the number of moles of solute, because that is what I need for my stoichiometric calculations. So I don't care about the mass or volume of solvent required to prepare a solution of required molarity, because all I am interested in is the amount or the number of moles of solute present in the solution for my stoichiometric calculations. So when I say sufficient amount of solvent or water, it doesn't bother me, because I am not interested in knowing the mass or the volume of water or solvent in general needed to prepare the solution. But I am very particular about the mass of solute or the number of moles of solute needed to make the solution. And with that, we can move on to the next question. What does it say? How many moles of solute are present in 50 milliliters of 0.1 molar solution of glucose? I think this is a very simple question. We are given the molarity of the solution, it is 0.1, and don't forget the units, 0.1 mole per liter. And we are given the volume of the solution in milliliters, but we need it in liters. So multiply it with 10 to the power of minus 3 to get its volume in liters. Then what is the expression for molarity? It is the amount of substance of solute or the number of moles of solute over the volume of the solution in liters. We know these two, substitute them here to get the number of moles of solute. So number of moles of solute or amount of substance of solute is equal to molarity multiplied with its volume. Molarity is 0.1 mole per liter multiplied with volume of the solution in liters is 50.0 times 10 to the power of minus 3 liters. These two get cancelled and simplify this to get the number of moles. What do we have next? What is the mass of ethylene glycol present in 120 milliliters of 0.4 molar aqueous solution? Now here the solute is ethylene glycol. So we are asked to find out the value of MB. And we are given the volume of the solution in milliliters. It is 120 milliliters. And in liters it would be 120 into 10 to the power of minus 3. And we are given the molarity of the solution. It is 0.4 mole per liter. Then how do you get the number of moles of solute? That is the number of moles of ethylene glycol present in 120 ml of this solution. You have to multiply molarity with the volume of the solution. That is 0.4 mole per liter multiplied with 120 into 10 to the power of minus 3 liters. Cancel these two and simplify this to get the amount of substance of ethylene glycol or the number of moles of ethylene glycol. But if you want the mass of ethylene glycol, given the number of moles or amount of substance, you have to multiply that with its molar mass. And because you know the molecular formula of glycol, it is given here, you can figure out its molar mass in gram per mole. Is it 24 plus 32 plus 6, 12, 62. So the molar mass of ethylene glycol is 62 approximately gram per mole. So you multiply the amount of substance with its molar mass to get the mass of ethylene glycol present in this solution. So what is NB? 0.4 into 120 into 10 to the power of minus 3 mole multiplied with 62 gram per mole. These two get cancelled and simplify this to get the mass of ethylene glycol in grams.